Hello students, welcome you all to my 9th video on the chapter alcohols, phenols and ethers, right? In the previous video we completed the discussion on phenols, the properties of phenols, properties due to benzene ring, all those things we discussed. In the today's video, one more important class of organic compounds under this particular discussion, that is ethers. Ethers are alkoxy derivatives. They are alkoxy derivatives of hydrocarbons. If one or more hydrogen atoms of given hydrocarbon are replaced by alkoxy group, that is alkoxy group is represented as OR, that is alkoxy group is what we call it as OR, or you can say that it can be OCS3, it can be OC2H5, this is what we call them as, it can be OC6H5, these are all alkoxy groups. When one or more hydrogen atoms of given hydrocarbon are replaced by alkoxy groups, you are going to get a class of organic compounds called, yes, it is ethers. Therefore, say for example, if I say this is hydrocarbon, RH, right? If one hydrogen atom of hydrocarbon, this is hydrocarbon, yes. If it is replaced by, yes, it is one alkoxy group, OR dash, for example. This is alkoxy group, OR dash, right? Then you are going to get R, O, R dash. So, and look at this. This is a class of organic compound called ether. So, the alkoxy derivatives of hydrocarbons in which the divalent oxygen, this is divalent oxygen, is attached with two alkyl groups or two aryl groups or one alkoxy, one aryl group, like that. That is what we call them as ethers. And that class of organic compounds is called as ethers. As far as ethers are concerned, this is ethers are functional isomers of alcohols. They are functional isomers of alcohols. For example, look at this. This is CH3CH2OH. This is alcohol with the formula C2H6O. Its functional isomer is what we call it as CH3OCH3. This is what we call it as ether. And its molecular formula is also C2H6O, right? This is molecular formula of ethanol and this is molecular formula of ether, and both are characterized by same molecular formula with different functional groups, and therefore they form functional isomerism. Or I can say, I'll go one example, that is, look at this. So this is what we call one of the alcohols, that is what we call as benzyl alcohol, right? This is benzyl alcohol. Its functional isomer is, that is what we call it as ether, right? And that is OCS3. This is, look at this, both are, yes, it is isomers with the same molecular formula, and of course this is alcohol and ether. Therefore, alcohols and ethers will form functional isomerism with the same molecular formula. Therefore, general formula of ethers is also CnH2n plus 2O. This is a general formula of alcohols as well as ethers. So that is something about introduction of this particular discussion, that is ethers, right? As far as the importance of ethers in our day-to-day life is concerned, ethers are very good solvents for various organic compounds, right? They can dissolve oils and fats, they can dissolve waxes, right? That, it is organic substances. That is one of the uses of this ether. Apart from that, this ether is very useful. This ether is very useful and it is used as anesthetic agent in various surgeries. Anesthesia, it will be used during surgery in order to avoid pain feeling for the patient, in order to prevent pain feeling for the patient, the patient will be given anesthesia. That ether will be used as one of the anesthetic agents. So that is what we call it as, ethers can be used as anesthetic agents. Okay, na? Apart from that, ether is very good solvent for Grignard reagent. Ether is very good solvent for Grignard reagent. A very useful reagent, that is Grignard reagent, used to prepare varieties of organic compounds, right? And the only solvent available for the Grignard reagent is ether. That is a solvent for ether. Apart from that, mixture of alcohol and ethers, and this mixture can be used as petrol substitute. It can be used as petrol substitute under the name nathalite. Under the name nathalite, this is what we call it as petrol substitute. That is, this mixture can be used as a fuel. And apart from that, ether, mixture of ether and dry ice, solid carbon dioxide, yes, mixture of ether and dry ice. is used as refrigerant. Is used as refrigerant in order to produce very low temperature of minus 110 degrees Celsius. So that much of low temperature can be achieved if the mixture of ether and dry ice is used, and that mixture is used as refrigerant. So these are the some applications of ether. These are the some applications of ether, and because of these advantages, it is very essential for you to understand what we call it as something about the chemistry of ethers. Under this particular discussion, we discuss something about nomenclature of ethers, classification of ethers, nomenclature of ethers, and of course preparation of ethers and properties of ethers, right? Now, let me start with the first discussion, that is classification of ethers. Classification of ethers. Depending upon the nature of R groups, they are classified into simple ethers. Depending upon the nature of R groups, they are classified into simple ethers, or you can say symmetrical ethers. They are classified as simple ethers or symmetrical ethers. Another is mixed ethers. One more type is mixed ethers, or you can say unsymmetrical ethers. And this is what we call it as one way of classifying ethers, right? In the case of symmetrical ethers, the nature of R groups will be same on either side of the oxygen atom. This is what we call it as simple ether, because this is CH3, this is also CH3, and of course symmetrical ether, or you can say that simple ether, or you can say that C2H5, C2H5. This is one more example for the simple ether. On either side of oxygen you have same type of, yes, it is alkyl groups, or you can go for, this is also an example for, yes, it is symmetrical ether, diphenyl ether. This is also one more example for the symmetrical ether or simple ether. And if the oxygen atom is attached with same kind of, yes, it is alkyl groups or aryl groups, and that will be called as what we call it as simple ethers, right? Whereas in the case of mixed ethers, and there will be two different alkyl groups or aryl groups will be attached to the, yes, it is oxygen atom. For example, in the case of mixed ethers, CH3O, C2H5, look at this. This is mixed ether or unsymmetrical ether, because on one side we have CH3 group, on the other side we have ethyl group, mixed ethers. Apart from that, we have CH3, CH2O, and of course CH2, CH3. This is what we call, here we have ethyl group, here it is propyl group. That is what we call it as mixed ether, right? Apart from that, we have CH3O, and of course phenol group. So this is also an example for mixed ether, because we have CH3 here, C6H5 here, different R groups are there, therefore they are all coming under mixed ethers. So this is what we call it as simple ethers and mixed ethers. Apart from that, ethers can also be classified as aliphatic ethers and aromatic ethers. And of course, I can give examples here only. This is aliphatic. This is aliphatic because the R groups are alkyl groups. They are aliphatic in nature. But this is aromatic because we have benzene ring here. If the ether contains a benzene ring, that will be called as aromatic ether. So this is also aromatic ether. Okay, now this is also aromatic ether, and remaining will be aliphatic ethers, right? So like that, we have aliphatic and aromatic ethers. Apart from that, ethers can also be of the type cyclic ethers. And of course, if the oxygen atom is involved in the formation of cyclic ring, that will be called as cyclic ethers. For example, here it is ethylene oxide. One of the, yes, it is cyclic ether. This is ethylene oxide. This is one of the, yes, it is cyclic ethers. This is CS2, this is CS2, right? Now I am writing bond line representation, yes. And one more, yes, it is cyclic ether, that is THF, we call it as popularly known as THF, that is tetrahydrofuran. This is tetrahydrofuran. So this is what we call it as example for cyclic ethers. Like that, the ethers can be classified into, yes, it is, we have one more class of ethers, that is what we call it as cyclic ethers, where the ethereal oxygen is involved in the formation of cyclic ring. So this is what we call it as classification of ethers. And this is the next discussion, right? And of course, we'll go for the IUPAC system as well as common system as far as nomenclature of ethers is concerned. In IUPAC system, they are alkoxyalkanes. They are named as alkoxyalkanes. And of course, the smaller alkyl group is named as alkoxy. bigger alkyl group will be named as alkane. I will come to know that particular aspect. Okay, na? So that is, we'll go for the one by one. First term, that is, first you write the table. We'll go for the first and the simplest one. It is CH3, OCH3. This is, yes, it is dimethyl ether, because in common names we name them as ethers, dimethyl ether, because two methyl groups attached to ether linkage, that is dimethyl ether, right? Here one is alkoxy, another is alkane. Yes, one is alkoxy, one is alkoxy, one carbon atom that is methoxy. That is methoxy because of one carbon atom in the alkoxy group, and it is in the parent carbon chain we have one carbon atom, therefore it is methoxymethane. Parent chain has got one carbon, two alla. Again, the parent chain is a one, which is a, yes, it is a long chain of continuous carbon atom. Continuous chain of carbon atoms. But here two carbon atoms are there, but they are not continuous. Therefore, only one carbon atom in the parent chain, that is methoxymethane, right? Next is CH3O parent chain. Therefore, it is in common system it is methyl ether. This is common name. In IUPAC system, this is methoxy and this is ethane. This is methoxyethane. As I said, the bigger alkyl group is named as alkane, that is ethane. This is bigger alkyl group, that is parent chain. Yes. Apart from that, we have CH3, CH2O, CH3, and CH2, CH2 and CH3. This is one more. Here it is ethyl, here it is propyl. This is smaller alkyl group, this is bigger alkyl group, therefore it is ethyl, common name, ethyl, propyl, ether. And of course in IUPAC system it is ethoxypropane, alkoxy, ethoxy, propane, because yes it is, there are three carbon atoms in parent chain. There are three carbon atoms in parent chain. Yes. So this is one more organic compound, right? Apart from that, we have CH3O and of course CH3. This is isopropyl group, right? This is methyl group and this is isopropyl group. Therefore, it is methyl isopropyl ether. This is common name is methyl isopropyl ether. Yes. What's the IUPAC name? And this is smaller is named as alkoxy. Bigger is named as alkane. Look at this, bigger has got three carbon atoms, and to the second carbon atom we have alkoxy group, that is 2-methoxypropane. To the second carbon atom methoxy group is connected, therefore it is 2-methoxypropane. Propane because of three carbon atoms in parent chain, ane because of carbon to carbon single bonds. That is what we call it as IUPAC names of some. Yes, it is the ethers wrap. Okay. Apart from that, we'll go for some more examples. Here it is one more ether where methoxy group is attached to benzene ring, and in common system it is called as yes, it is methyl phenyl ether. Methyl phenyl ether. This is methyl group, this is phenyl group, methyl phenyl ether. In IUPAC system it is methoxybenzene. Because we have treated it as a, that is benzene ring as a parent here, because it contains more number of carbon atoms. Therefore, it is methoxybenzene. Benzene contains more number of carbon atoms. Therefore, it is taken as a parent chain. Look at this. It is ethyl phenyl ether. It is ethyl phenyl ether. This is ethyl group. This is phenyl group. Ethyl phenyl ether in common system. It is also called as phenatol. Its common is phenatol antanu karitare. Methyl ethyl ether anna anisole antanu karitare. This is also known as anisole, right? In IUPAC system it is ethoxybenzene. This is ethoxybenzene. Here also benzene ring is taken as parent due to the presence of larger number of carbon atoms, right? More number of carbon atoms, right? Look at this. Here we have two, yes, it is sites, R groups on either side of the oxygen, right? This benzene ring contains 6 carbon atoms. This side chain contains 7 carbon atoms. Therefore, this will be treated as a parent now. Heptyl group is treated as a parent. Benzene ring is treated as a substituent. because it contains more number of carbon atoms, 7. Here it is 6. And of course in common system it is, yes, it is heptyl because 7 carbon atoms, heptyl phenyl ether. Heptyl phenyl ether is a common name, right? In IUPAC system it is phenoxyheptane. That is heptoxybenzene allyl. Next, ethoxybenzene allyl. It is phenoxyheptane because your benzene ring is taken as substituent. That's why it is phenoxy. Your C2H5 is taken as substituent. Therefore, it is ethoxy. Your C6H5 phenyl group is taken as substituent with less number of carbon atoms compared to heptyl. Therefore, heptyl is treated as a parent. Therefore, it is named as heptane. Look at this here. This has got 6 carbon atoms and this has got 5 carbon atoms. So which is parent? Benzene is a parent, right? And therefore it is common name in that is phenyl. Yes, it is 5 carbon atoms. It is pentyl, CH3CH in the isopentyl ether. This is the common name. What is the IUPAC name? I said this benzene ring is taken as a parent now. This will be treated as a substituent. Okay, na? And here it is how to name this particular substituent. Andre, this is 1, this is 2, this is 3, this is 4. Okay, now if CH3 is not there, it will be butoxy. If CH3 is not there, it is butoxy. CH3 irodrinda at third position 3 methyl. At third position we have methyl group. Howda? 3 methyl butoxy. 3 methyl butoxy benzene. 3 methyl butoxy benzene. These are the IUPAC names and common names of certain, yes, it is ethers. Then apart from that, we'll go for some cyclic ethers. Right? For example, this is one example. Yes, this is, and of course, yes, it is one more. One example for the cyclic ether, right? Look at this. This is derivative of cyclohexane. Here it is 2 methyl groups and it is ethoxy group. 1, 2. Ethoxy group. This is number 1 and this is number 2. Yes. Therefore, it will be named as 2-ethoxy. IUPAC name I am writing. This is ethoxy, 2-ethoxy, 1, 1 dimethyl. Dimethyl, because at first position we got 2 methyl groups and then it is cyclohexane. ನೀವು ಹೀಗೆ ಕೇಳ್ಬೋದು ಬೇಕಾರೆ ಸರ್ ಇದಕ್ಕೆ ನಂಬರ್ 1 ಕೊಟ್ಟು ಇದಕ್ಕೆ ನಂಬರ್ 2 ಕೊಟ್ರಿ ರೈಟ್ ಅಕಸ್ಮಾತ್ ಇದಕ್ಕೆ ನಂಬರ್ 1 ಕೊಟ್ಟು ಇದಕ್ಕೆ ನಂಬರ್ 2 ಕೊಡಬಾರ್ದಾ ಸಮ್ ಆಫ್ ದಿ ಲೊಕೆಂಟ್ ಸೇಮ್ ಆಗುತ್ತಲ್ಲ ಅಂತ ನೀವು ಕೇಳಿದ್ರೆ ನೋಡಿ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಇಫ್ ಐ ರಿವರ್ಸ್ ದ ನಂಬರಿಂಗ್ ಸೆಕೆಂಡ್ ಏನಾಗುತ್ತೆ ಮಿಥಾಲ್ 2 ಇದೆ 2 + 2 ಆಗುತ್ತೆ ಇದೆಯಾ ಇಥಾಕ್ಸಿ 1 ಇದೆ ಅದೇನಾಗುತ್ತೆ 1 ಇದೆ therefore it is 5 ಆಗುತ್ತೆ ಇಫ್ ಐ ರಿವರ್ಸ್ ದ ನಂಬರಿಂಗ್ ನಾನು ಈ ರೀತಿ 1 ಫಸ್ಟ್ 1 ಅನ್ನ ಮಿಥಾಲ್ ಕೊಟ್ಟರೆ ಏನಾಗುತ್ತೆ 1 + 1 + 2 ಎಷ್ಟಾಗುತ್ತೆ 4 ಆಗುತ್ತೆ ನೋಡಿ some of the locations will be different ಹಾಗಾಗಿ which is preferred one should be given to the yes it is methyl group there okay na and that is what we call 2-ethoxy 1 dimethyl cyclohexane right yes akasmat ಹೀಗಿದ್ರೆ ನೋಡಿ this is one and of course ಹೀಗಿತ್ತು ಅಂತ ಇಟ್ಕೊಳ್ಳಿ ಒಂದೇ ಮಿಥಾಲ್ ಗ್ರೂಪ್ ಇದೆ ಇಲ್ಲಿ ಒಂದು ಮತ್ತೆ ಓಕೆನಾ ಈಗ 1 ಆಯ್ತು ಇದು 2 ಆಯ್ತು ಓಕೆನಾ ಸಮ್ ಆಫ್ ದಿ ಲೊಕೆಂಟ್ಸ್ 1 + 2 ರಿವರ್ಸ್ ಮಾಡಿದ್ರೆ 1 + 2 ಅದು ಕೂಡ 1 + 2 ಆಗುತ್ತೆ 3 ಆಗುತ್ತೆ ಸಮ್ ಆಫ್ ದಿ ಲೊಕೆಂಟ್ಸ್ ಹೌದಾ ಆದ್ರೆ ಯಾವ್ದು ಪ್ರಿಫರ್ ಮಾಡ್ತೀನಿ ಈಗ ಅಂದ್ರೆ 1 should be given to the ethoxy because if the sum of the locants is same in both the directions ಏನಾಗುತ್ತೆ then you have to follow the alphabetical order 1 ethoxy 2 methyl 1 ethoxy 2 methyl cyclohexane because of the 6 carbon atoms inside cyclic ring ಗಮನಿಸಿ ಇಲ್ಲಿ I have not followed alphabetical order rule ಹೌದಾ but here I am following alphabetical order rule ಹೌದಾ numbering is on the basis of alphabetical order but here is not according to alphabetical order ಯಾಕೆ ಅಂದ್ರೆ if I follow the alphabetical order some of the locants will be different because of that so you need to follow that lowest sum rule and if I give number 1 and number 1 to the methyl group 2 to the ethoxy group some of the locants will be minimum and therefore it should be 2-ethoxy 1 dimethyl cyclohexane But here some of the locants will be same on either side of the in both the directions, and therefore it will be alphabetical order to be followed. 1-ethoxy-2-methyl cyclohexane, right? Apart from that, example in your NCERT group, NCERT book, the two ether linkages, that is CH2 and that is CH2, and it is OCS3, right? OCS3 and it is OCS3. This is a compound with two ether linkages, right? Then it is 1 and number 2, that is 2 carbon atoms in parent chain. Therefore it is 1,2 dimethoxy, 1,2 dimethoxy-ethane. Ethane because of 2 carbon atoms in parent chain. 2 carbon atoms in parent chain. 1,2. First position we have methoxy. Second position we have methoxy. 1,2 dimethoxy-ethane. So this is what we call it as IUPAC names of different ethers. IUPAC names of different ethers, right? So that is what we go for that. Structure of ethers. I already said structures of alcohols, ethers and phenols will be obtained from water. Look at this, I got water using H2O with the 2 lone pairs on the oxygen, or the bond angle of, yes, it is 104.5 degrees. This is water, yes. And oxygen atom is sp3 hybridized. Oxygen atom is sp3 hybridized, right? And you can get ether, yes, if 2 hydrogen atoms are replaced by 2 R groups. Now you can say that this is R and it will be R, yes. If 2 hydrogen atoms are replaced by, yes, 2 R groups, and you are going to get ethers with 2 lone pairs on the oxygen atom. Look at this, oxygen atom is sp3 hybridized, right? And of course we expect that bond angle to be, yes, it is bond angle to be 109 degree 28 minutes, right? But in the case of ethers it will be 111.7 degree. Bond angle is increased to 111.7 degree. Look at this, that bond angle in ethers is slightly greater than the regular tetrahedral angle, because you know R groups are very bulky. R groups are bulky. They are very bulky groups. They occupy more space. They occupy more space. Then what happens? You know, there is a repulsion. There is a repulsion among the bulky. E groups bulky ಆದ ತಕ್ಷಣ repulsion ಆಗಿಬಿಟ್ಟು bond angle ಜಾಸ್ತಿ ಆಗುತ್ತೆ. Yes. Therefore, bond angle is increased from 109 degree 28 minutes to 111.7 degree. So, okay, na? So that is what we call it as the bond angle and the structure of, yes, it is ethers, and of course here the oxygen atom is sp3 hybridized, right? So with that, you know, we'll go for the next topic, that is, and of course different methods are available for the preparation of ethers, correct and nodಕೊಳ್ಳಿ. Very important discussion for the examination point of view, right? The first discussion is of course preparation from alcohols. Preparation from alcohols, and that is by dehydration. That is by dehydration, yes. By the method called dehydration, yes. Dehydration involves removal of water, yes. Look at this, when ethyl alcohol, yes, and this is ethyl alcohol athwa ethanol, when it reacts with, when it is heated with concentrated sulfuric acid, when it is heated with concentrated sulfuric acid, yes, when it is heated with concentrated sulfuric acid, one of the dehydrating agents, right? At low temperature, that is 413 kelvins, right? At low temperature, like 413 kelvins, look at this, dehydration takes place like this between 2 ethanol molecules. This is one ethanol molecule, this is another ethanol molecule. Therefore, we use here excess ethanol we use, right? And dehydration takes place between 2 ethanol molecules, and that results in the formation of diethyl ether, and of course plus H2O, and this is diethyl ether. This is diethyl ether, right? If you remember the previous discussions under alcohols, when ethanol is heated with concentrated sulfuric acid, right, at about 443 kelvins. So remember this. When same ethanol, when it is heated with, yes, it is concentrated sulfuric acid, here also dehydration takes place, but you got, yes, it is CH2 double bond CH2, and of course plus H2O, right? Here it is CH2 double bond CH2 plus H. You got, here it is ethene, you got. As why I am giving this particular reaction, because If this reaction is carried out at low temperature, you are going to get ethers by the reaction called substitution. This reaction is substitution, and of course especially it follows SN2 mechanism. Nucleophilic substitution reaction of order 2. That is substitution reaction at low temperature. If I increase the temperature, right? If I increase the temperature, yes it is. The reaction follows elimination reaction. The reaction will be elimination, right? Reaction will be elimination, because when the temperature is high, that you are going to get carbocations. You are going to get carbocations are produced. When the temperature is raised, ethanol is converted to ethyl carbocation. When ethyl carbocation is formed, elimination is preferred. When carbocations are produced, elimination is preferred. Therefore, in this particular reaction, there is always a competition between elimination and substitution. If you want that ether in this reaction, you need to favor substitution reaction. Therefore, you maintain low temperature. If you want to bring about, if you want to get alkenes, you favor elimination reaction and you maintain high temperature. Because at high temperature, alcohols produce. At high temperature, alcohols produce. What is that? Yes, it is carbocations. At low temperature, and of course, carbocations are not produced. Rather, there is a SN2 mechanism reaction. Therefore, if you want ether in this reaction, you go for excess ethanol at 413 degrees, 413 kelvins in presence of dehydrating agent, and you are going to get ether there. Yes. Okay, now? Yes. And remember, this method is suitable only for the preparation of ethers with primary alkyl groups. This method is suitable to prepare ethers with primary alkyl groups. Ethers with primary alkyl groups. You know the primary alkyl groups are there? It is CS3 and that is CS2. CS3, this is primary, or you can say CS2 and it is here. These are all primary alkyl groups. If you want to prepare ethers with secondary and tertiary alkyl groups, this method cannot be used. Andre substituted ethers with branched alkyl groups cannot be prepared by using this particular method, that is starting from alcohols. Okay na? And before that, we'll go for the mechanism of this particular reaction. That is mechanism of conversion of ethanol to ether. Now it is the dehydration of ethanol to ether. This is SN2 mechanism. Ethanol to ethene madbekare, you produced carbocation. That is SN1 mechanism. But here it is ethanol to ether only. Carbocation is not produced. Okay na? Carbocation is not produced, right? The first step is, protonation of ethanol. And this is ethanol with 2 lone pairs on the oxygen in presence of concentrated sulfuric acid. And of course, lone pair of electrons on the oxygen will absorb H plus, and that results in the formation of, CS3, CH2, and it is OH2 plus. This is OH2 plus. H plus is taken up by OH, and therefore OH2 plus, you are going to get oxygen is having plus charge because it has lost electrons to H plus ion. This is first step. CS3, CH2, OH2 plus, right? Okay now? In the second step, right? Yes, it is. We have one more molecule of ethanol, right? That attacks this. Yes, it is. That the product of the first step, notice. This is a product of the first step. I just write like this just for the convenience. OH2, then attached to CS2, CS, right? Just for the convenience, right? And this is lone pair of electrons on the oxygen, and of course due to the presence of positive charge on the oxygen, electrons are moving towards oxygen, right? Because oxygen is first of all electronegative and with positive charge, yes. Okay na? Then electrons will be moving towards oxygen, and this will be OH2 will be taken out in the form of H2O, that creates plus on the carbon, and of course O will attack this carbon. That's what you observed in the case of SN2 mechanism, right? And then it results in, this is a slow step, right? And of course this is CH3, CH2, CH3, CH2. O is attached to C. O loses electrons, therefore it becomes O plus. After losing electron, O becomes O plus. To this, hydrogen is attached. O is connected to CH2 there. CH2 and it is CH3 plus H2O. This is OH2 plus is taken out in the form of H2 over there. This is second step. In the third step, look at this. The product of the second step, right? Right, the product of the second step, right? And this is CS2, CS3, right? Positive charge is there in the oxygen, therefore it attracts sigma electrons towards this. Hydrogen is taken out in the form of H plus, and positive charge is neutralized. And of course, you are going to get CH3, CH2O, CH2, and it is CH3 along with the formation of H plus. So this is what we call it as ether, diethyl ether, right? So you started with ethanol. You started with ethanol, and of course this is what we call it as mechanism of conversion of ethanol to ether, right? Okay na? So this is the mechanism. Agboda, right? Artha aitu ankotini. So nenpidukobekili, the mechanism follows SN2 mechanism because here the reaction doesn't involve the formation of carbocation. If carbocation is formed during a reaction, enagutte, elimination takes place and you are going to get alkenes. That's what you observed in the dehydration of ethanol to ethene. Yes, but here this is SN2 mechanism. No formation of carbocation here, and of course there is a SN2 mechanism. You are going to get intermediate, that is, this is what we call it as transition state you are getting, and that is what we call it as the mechanism of dehydration of ethanol to ether. And I said, so starting from alcohols, you may not prepare, you cannot prepare, yes it is the ethers with branched alkyl groups. For that purpose, you should go for the one more method, that is what we call very, very useful method for the preparation of alcohols, that is Williamson's ether synthesis. So this is Williamson's ether synthesis, very useful method for the preparation of ethers. It can be used even to prepare ethers with branched alkyl with primary, secondary alkyl groups, right? Primary, secondary and tertiary alkyl groups, right? Well, write the general equation first. When, yes it is haloalkane, this is haloalkane, RX. And then an haloalkane, right? When it reacts with sodium alkoxide, NaO R dash, this is sodium alkoxide. Go to that. OR and then alkoxide, sodium alkoxide, yes. And that results, right? Yes, it is substitution takes place. RO R dash. And of course plus NaX, and this is what we call it as ether. This is what we call it as Williamson's ether synthesis, and this is general equation for the Williamson's ether synthesis, right? For example, if I want to prepare, yes, CH3O, yes it is CH2, CH3 plus, either non prepare ಮಾಡಬೇಕಂತ ಇಟ್ಕೊಳ್ಳಿ, right? This is ethyl methyl ether ಅಥವಾ methoxyethane. I want to prepare this ethyl methyl ether, yes. Then R is equal to CH3, R dash is equal to C2H5. Oh, the R is equal to CH3, that is, and CH3Br, methyl bromide, yes. X can be any halogen atom, plus NaO, R dash N, CH2 CH3, this is bromomethane, this is bromomethane, this is sodium ethoxide. This is sodium ethoxide, right? And of course NaBr is taken out. You are going to get this compound plus NaBr, right? This is methoxyethane. Methoxyethane. Athava ethyl methyl ether, right? Illodi. R is equal to CH3 hakide. R dash is equal to C2H5. Reverse ಮಾಡಬೇಕಾರೆ. R is equal to C2H5 ಹಾಕಬೇಕಾರೆ. That is CH3 CH2Br. ನೋಡಿ. R ಇಲ್ಲಿ CH3 ಇಲ್ಲಿ ಏನಾಗಿದ್ದೀನಿ CH3 CH2 R change ಮಾಡಿದ್ದೀನಿ. This is bromoethane and this is bromoethane, yes, plus now R dash is CH3 NaO CH3, that is sodium methoxide, yes. then also you are going to get, yes, it is CH3, CH2O, CH3 plus NaBr. So this is methoxyethane once again. This is methoxyethane. Methoxyethane once again. And then methoxyethane can be obtained either by using bromomethane or yes, it is bromoethane. If bromomethane is used, you are going to get, you should use sodium methoxide. If bromoethane is used, you are going to get sodium, you should use sodium methoxide here. Just by changing R groups, you can prepare any type of ether compounds. You can prepare any type of ethers, and this is what we call it as Williamson's ether synthesis, right? And of course, one of the advantages of this particular method is you can prepare, yes, it is ethers with secondary and tertiary alkyl groups. Athwa you can prepare ethers with the branched alkyl groups can be prepared, yes, it is starting from Williamson's ether synthesis. How it is, we'll see, right? Or yes, it is RX, you know this, RX plus NaO R dash, and that gives RO R dash plus NaX, right? Okay, now I want this branched alkyl group, right? CH3. Yes, it is CH3O, and it is CH3, and of course CH3, and of course CH3 plus. I want this ether. R is CH3, R dash is tertiary butyl group. Yes. ಸ್ವಲ್ಪ ಗಮನಿಸಿ ನಾನು ಬರೆಯೋದನ್ನ. ನನಗೆ I want to have this ether with branched alkyl groups. So ಏನಾಗುತ್ತೆ? R is equal to CH3, right? CH3Br, yes. Bromomethane plus NaO, R dash ಬದಲಾಗಿ ಏನು? CH3, and it is CH3, right? And this is what we call it as bromomethane. This is bromomethane. This is sodium tertiary butoxide. Sodium tertiary butoxide, and of course NaBr ಆಗುತ್ತೆ. And now you are going to get, this is the product. This is, yes, it is 2-methoxy, 1, 2, 3, 2-methoxy, 2-methyl. Yes, it is 3 carbon atoms, therefore it is propane. This is what we call it as the product you got there. Yes. Agboda? Andre, when bromomethane reacts with sodium tertiary butoxide, you are going to get 2-methoxy, 2-methyl propane. Yes. If I reverse it, right, look at this. Here I got primary alkyl. Instead of that, I will go for tertiary halocane, tertiary butyl bromide plus NaOCH3, NaOCH3, right? And we expect this. This is expected. ನೋಡಿ, just ಈ ತರ ಮಾಡಿಬಿಟ್ರೆ ನಿಮಗೆ ಏನು ಸಿಗುತ್ತೆ? You got this CH3 tertiary butyl group oxygen, CH3 tertiary butyl group oxygen. This is expected, yes. But actual product is this CH3, and of course CH2, and of course this is CH3 plus NaBr plus CH3OH. This is the product. This is 2-methyl propene. 2-methyl propene. This is 2-methyl propene. Andre ಇಲ್ಲಿ ನೋಡಿ ಗಮನಿಸಿ. If you want to prepare a ether with the branched alkyl groups, you must use primary haloalkane so that you can promote SN2 mechanism. You know, primary haloalkanes are more reactive towards SN2 mechanism. If I use tertiary haloalkanes, they produce tertiary butyl carbocation, that is, they produce stable carbocations. ನೋಡಿ, ನಾನೇನಾದ್ರು tertiary haloalkane ಯೂಸ್ ಮಾಡಿಬಿಟ್ರೆ ನೋಡಿ, you are going to get, this is tertiary butyl bromide, yes, okay na? That produces tertiary butyl carbocation. Yes. Tertiary butyl carbocation produce ಮಾಡಿದ ತಕ್ಷಣ look at this OCH3 minus. ಇದೆಲ್ಲಿಂದ ಬಂತು? This is OCS3 minus. This will absorb, nodi. This will absorb H plus. OCS3 minus is absorbing H plus. Now sigma electrons are moving towards this. Again, we're going to get CH3, and of course single bond is converted to double bond. Yes, it is CH3 plus CH3OH. Now here it is acting like a base. This OCS3 minus is acting like a base because base absorbs H plus. Here in this case, this alkoxide group, tertiary butyl oxide group, tertiary butyl alkoxide group, tertiary butyl oxide group, it will be acting like a nucleophile. It will be acting like a nucleophile. And therefore, if you want to prepare ethers with branched alkyl groups, you prefer primary haloalkanes. If tertiary and secondary haloalkanes are used, okay na? If the tertiary and secondary haloalkanes will produce the stable carbocations, formation of carbocations will lead to the elimination reaction. Like this, your stable carbocation barutte, it will lead to the elimination and you are going to get alkene. Therefore, if tertiary and secondary haloalkanes are used, and you are going to get alkenes. If primary haloalkanes are used, you are going to get, yes, it is, what is that? Ethers you are going to get. Idana salpa gamanisbeku hagagi. So whenever you are asked to prepare substituted, yes, it is substituted, yes, it is alkyl groups, that is ethers with substituted alkyl groups, then you have to go for primary haloalkanes, and of course substituted alkoxide you have to use. You have to use substituted alkoxide or branched alkoxide you have to use, right? So this is what we call it as preparation of ethers. Okay now, and of course even this Williamson's ether synthesis can be ether, conversion of phenol to ether, right? Now I go for this phenol, and this is OH. When it reacts with sodium hydroxide, yen barutte? Yes, it is, H plus phenol in the OH minus sodium hydroxide in the, then you are going to get sodium phenoxide. So when it reacts with, yes, it is RX haloalkane, right? Okay, now this is Williamson's ether synthesis, right? NEX is going out, and you are going to get alkoxybenzene, OR, yes, you can see that is OR plus NEX. You are going to get ether there, alkoxybenzene, aromatic ether, yes, that is conversion of phenol to ether, yes. Phenol has to be converted to, yes, it is sodium alkoxide, okay, now sodium phenoxide by using sodium hydroxide, and then it is converted to, yes, it is, that is ether there. But yes, it is, if I go for this, if I use this reaction, look at this. This is, nodi, that is, ಇಲ್ಲಿ sodium phenoxide use ಮಾಡ್ತೀನಿ, ಇಲ್ಲಿ sodium alkoxide with ಇಲ್ಲಿ haloalkane, but ಇಲ್ಲಿ halohalide use ಮಾಡ್ತೀನಿ. Will you get this product? ಈ ತರ ಆಗುತ್ತಾ? Will you get this product? Yes, ಬರುತ್ತಾ? If I use haloarine, will you get this product? No, reaction not possible, because in the case of haloarenes, ಏನಾಗುತ್ತೆ? There is a double bond character between carbon and halogen, and they do not undergo nucleophilic substitution reactions easily. Therefore, in order to prepare this alkoxybenzene, you must use sodium phenoxide and of course primary haloalkane. Yes, and you cannot use haloarenes ether synthesis for the preparation of, yes, it is ethers. You must use haloalkanes, right? So this is what we call it as preparation of ethers, that is by Williamson's ether synthesis. Artha aitu ankotini, right? And that's all for now. We'll see in the remaining things in the next class, right?